This is a black hole, simulated in C++ using OpenGL. Black holes are amongst the strangest objects in the universe. With the ability to bend light in front of your very own eyes, these are some of the most mathematically complicated things in the entire universe that we have yet not fully understood. Though in this video, I'll show you just how these crazy objects work using real physics equations to simulate the effects of black holes in space. To start, let's create a blank window using GLFLW. Next, we can create a struct to hold all the data we need to create the black hole, with one of the most important being the event horizon, or this RS here, or the point that not even light itself can return, creating the black spherical object we know as the black hole. Next, we can create a draw function that creates a list of vertices that forms the shape of a circle, which OpenGL can convert into separate triangles, creating a circle. Now we can create a rays function, which from a single point scatters a bunch of light rays facing towards the black hole. Now we can actually add some physics into it that alters the path of the rays. But before we do that, we need to explain some things. So you probably heard that the universe is made up of space-time, and big masses, or for anything this matter, can curve it. But if you look at 2 points on a curved globe, and then take those same 2 points, but then put it on a flat map, it appears to be curved. Yet it's actually the straightest possible lines being converted from a globe to a flat map. This is called a geodesic, or the shortest path on a curved surface. This goes the same for space-time, and all matter and light follows the geodesic path. So what we need to do now is make these light rays follow the geodesic path around the black hole. So right off the top, you might be thinking of just using Newtonian gravity or applying a force. But we actually need to calculate the shape of the space-time around the black hole and the non-geodesic, which is a special path that massless particles like photons take. So the formula we need is the Einstein's field equation. But in order to do this, we need very specific conditions, which is incredibly hard to do. So that's why Carl Schwarzschild created the Schwarzschild solution, which makes our lives a lot easier. Schwarzschild solved Einstein's field equations for the specific case of the spherical non-rotating mass, which is good enough for the approximation of most black holes. What he found describes exactly how the space-time curved around the mass. From that, reducing down a lot of heavy math, the path of a photon ends up as one of the surprisingly clean equations called the Beignet equation, which looks like this. Adding this into our project using the Runecuda 4 or RK4 design, we can see it works perfectly. But 2D is cool and all, but 3D would look really cool. So let's get started. The really cool part is that even though that we're in 3D now, the math barely changes at all. We just find the plane each light horizon and run the exact same Beignet equation we already wrote inside it. We also add a proper 3D camera with a yaw and pitch so you can fly around and look at the black hole from any angle. But there's one slight problem when moving to 3D. We need a lot more rays, like a lot more. And each of those rays have to go through a bunch of tiny steps, including the RK4, which is really not good for performance. In fact, if you tried to run this, it would guaranteed just crash. So in order to fix this, we need to set up something called a quad texture. What we do is create a big array of pixels, just RGB color values. Then each of those pixels, we shoot out a single ray from the camera onto the scene, trace it through the curved spacetime using our Beignet equation, and whatever it hits, we write that color onto the array. Once we've filled up the whole array, we slap it onto a texture and draw that texture onto a big quad that covers the entire screen. Now the other trick is we don't actually have to ray trace at the full window resolution. We can ray trace at something like 200 by 150, which is way less pixels to trace. And now the last thing we add is the accretion disk. This is the glowing ring of superheated gas orbiting just outside of the event horizon. And it's what makes the whole thing look so iconic. And the really cool part is we never actually draw it as the geometry at all. We just checked during the ray integration whether the photon crossed the equatorial plane inside the disk radius, and if it did, we just add an orange glow to the pixel. And that is what gives us the final product, the black hole. I thank you everyone for watching this video. I spent a really long time on it, so it would mean the world if you could like or subscribe. But anyways, have a fantastic day.